Good morning, everyone. We come to this lecture that I'll try to introduce the band structure of a monolayer MoS2 in this lecture. So I prepared some lecture slides, and it is on how we can understand the material of MoS2, and then from the material of the slide, we try to build an effective model for calculating the band structure near the band edges. That means near the K or K prime points. So we start from something basic. We start from something basic. So first, we look at the periodic structure. So in this periodic structure, okay, so in this periodic structure, where's MO? MO means molybdenum disulfide. Okay, so this MO atom, if you check the information, molybdenum has an atomic number of 42, and the atomic weight is 95.95. And this is the electron configuration. This is the electron configuration. So from this configuration, we can have some information about what contribute to the band structure of molybdenum disulfide. So for now, we don't need to worry about the sulfur atom yet. Okay, the main contribution to the band structure near the K and K prime values are from the molybdenum atom. Okay, so and the molybdenum electron configuration has this representation. So krypton is the atom here. This is krypton. It represents the fully filled shell configuration. You know this krypton is something like the neon, helium, argon. They are inert gas. Okay, so once they form a complete shell, usually they don't contribute to the chemical potential. So all we need to worry about is the electrons beyond this complete shell. So there are totally 6 electrons available. So from here, you can already see 1 S, 1, 2, 3, 4, 5 D electrons. Okay, so totally 6. So if you show the energy of these different shells, so this is the energy, this is the electron configuration at different energy levels. So this energy is not to scale, but you kind of know their relative position. So the relevant electrons is on the 5s shell and the 4d shell, totally 6 of them. Okay, any questions? So these d orbitals are important to understand the electronic properties of MoS2. So these are the shape of the d orbitals. So you have learned some basic knowledge of angular momentum in quantum mechanics. So if you plot the harmonic function of the d orbit, then there are totally 5 of them. So this z square, yz, xz, xy, x square minus y square, those are the representation name of this orbit. So they basically represent the symmetry property of this orbit. For example, Z2 means plus Z and minus Z direction, they are the same. Okay, you flip the Z direction, then the orbit is the same. Okay, so you can already see that from the shape, right? So if you flip it on the Z direction, it's the same. So YZ means if you change the sign of Y, you're going to change the sign. So for example, here, Y is plus Y. You have the Y and red color. If you flip to the negative sign, you flip the color. So basically, the color represents the sign of the wave function. If you flip the sign on Z, you also have the change of sign of the wave function. But if you change the sign of X, then you're not going to change the wave function sign. Okay, so the same for XZ. If you change X or Z sign, the wave function is going to flip sign. If you change the Y sign, it's not going to change the sign. Okay, the same for X and Y. And X squared, Y squared, what does it mean? That means if you are in a direction like in the direction diagonal. Okay, diagonal of it, x minus y, like in the diagonal direction in the xy plane, you're going to flip the sign. Because you change x to y, y to x, you're going to flip the sign. Okay, so you can see that there are 5 of them. They have different symmetry property. Okay, I think the figures are more easy to visualize. Okay. Of course, when you have a 3D, 4D, 5D, you're going to have different radial function. So the shape will look more complicated than that. But the angular direction, the symmetry property in the angular part is the same. Okay. So one important property is that all these 5D orbitals, they have the same energy if the molybdenum atom are isolated. That means if it has a spherical symmetry, then all these 5 are energy degenerate. Okay. So you can separate these 5 states into 3 groups, 3 sets. The first set is you use the LZ, the Z component of the angular momentum as the quantity. So for m equal to 0, then this is the dz squared. Okay. Then so this 0 means that m is 0. D0 is dz squared. Okay. The second group is when m is plus or minus 1. You need to know that dxz and dyz, they are not eigenstates of LZ. But the linear combination of them can become the eigenstate of LZ. So the combination is this chiral combination, plus and minus I times dz. I mean, because m plus 1 means they're rotating in this way. Minus 1 means they're rotating the other way. But from this wave function, you see that it's not really a rotating function, right? Like, I mean, at least the feeling doesn't tell you that they're rotating. But once you make this combination, then they will give you a rotating wave function. Okay. It is a little bit like the polarization of light. You have a linear polarization X, linear polarization on Y. If you combine them without using the I, then they just give you another linear polarization. But if you use X polarization plus or minus I, Y polarization, then you give you a circular polarization, similar. Okay, so if you use the wave function to represent it, then dxz plus or minus I dyz with a normalization factor 1/2 square, then this will give you d plus or minus 1. So this is the way they combine to give you the m equal to plus or minus 1. Okay. Then the third group is when m equal to plus or minus 2. So it is dx squared minus y squared plus or minus I dxy. So if you do it in this way, then you get the eigenstates of LZ for m equal to plus or minus 2. So these are some basic about the wave function of the angular momentum operator. If you want to know the details, you can review the contents in the textbook of quantum mechanics. Okay, so once they okay, you can use m to group them into these 3 groups. Okay, okay. So now let's come to the lattice. So let's say you are not considering isolated molybdenum atom. You're considering molybdenum atom as a part of the lattice. So monolayer MoS2 has this lattice structure that I show here. If you see for the first time, you probably are confused what is the structure. So if you look from the top, you see a honeycomb lattice. This is the MO atom, this is the selenium atom, but there are 2 selenium atoms. If you look it from the top, you only see 1. But if you look at this side, you see there's 1 on top, the other on the bottom, and this one is connected to the top and the bottom. So from the top is a honeycomb lattice, but each selenium atom has a top and bottom atom. So it is a honeycomb lattice from the top, but from the side it has the top and bottom. So if you look at the lattice, let's look at the situation of 1 molybdenum atom. If you look at the situation of 1 molybdenum atom, so this blue-green atom here is the molybdenum atom. and it is surrounded by 6 selenium atoms, 3 on the top, 3 in the bottom. Okay, and it is connected to the top with 3 bonding, and to the bottom also with 3 chemical bonds. So each molybdenum atom is bonded with 6 sulfur atoms. Okay, if you just connect this AS atom with a line, these are just the lines that help you to understand the structure. They are not chemical bonds. These are the chemical bonds. These sticks on this part are the chemical bonds. These lines are just some a line to help you to understand the structure, the shape. They're not chemical bonds. So these are chemical bonds. These are just lines that I draw. I didn't draw it. I just copied this figure to help you to understand that this is a trigonal prism. You know what the prism is, right? You use a prism in the lab. Trigonal prism means the top surface and the bottom surface are a triangle. Okay, so they form a trigonal prism. So the S atom forms a trigonal prism, and the MO atom, the molybdenum atom, is at the center of the trigonal prism. So this MO atom, it has this structure has two symmetries. One is the mirror reflection symmetry. That means you change the Z to plus Z to minus C, then you're going to get the same thing. So it has a mirror reflection symmetry. Okay. Another symmetry is the threefold rotational symmetry. If you rotate it for 120 degrees once, twice, you're going to get the same thing. Okay. Is that okay? Okay, let's continue. Okay, so let's look at how different d orbits will be affected by the trigonal prism of the sulfur atoms. Okay, if you look at the dz square, the m equal to 0 orbit, okay, so the shape is like this. But if you compare that with dz dyz, dyz is not m plus or 1 or minus 1. You need a linear combination with the other one. Okay, but if you just look at here, you can already see that these two orbits, they're very different, right? You can already visualize that they will be affected by the S atom in a different way. Okay, if you also check this dxy, is also different. The relative orientation, the distance between the S atom and this orbit, electron position, they're all different. So you can already see that these 3 kind of orbits will be affected by the S atom in a different way. So you will expect that these 3 orbits, they will shift in different energy. If you use the first order perturbation theory, you have the perturbation, you have the wave function, you take an inner product, you get the energy shift. And you can already see that these 3 will give you 3 different energy shifts. Okay, because they are obviously different. However, if you compare dyz and dxz, you compare these two, they are both their linear combination will give you m plus 1 or minus 1. But you look at these two, they will have the same effect because the orientation of these two are just rotated by 90 degrees. Okay, it just rotated by 90 degrees. When you rotate it by 90 degrees, a trigonal warping, sorry, not trigonal, trigonal prism, if you do the perturbation theory, you just get the same energy. You get this, just get the same energy. Actually, it's not just by perturbation. They have the same energy. You can actually prove this by using the symmetry property by group theory. Okay. Similarly, if you go to the m equal to plus minus 2 orbit, like this 2 component function dxy, dx squared minus y squared, these two are also just rotated by 90 degrees. Not 90 degrees, it's 45 degrees. Okay, they will also have the same energy. Okay, I mean, you can use group theory to show it more rigorously, but here I think using the graphics is more easy to visualize. Okay. Okay, so basically, for isolated MO atom, you have 5 4D electrons. They are all energy degenerate when they're isolated. Okay, but once you put the MO atom at the center of this trigonal prism of the S atom, they will split into 3 energy levels. Okay, so the first set is the M plus or minus 1. These two will have 1 energy. M plus equal to plus or minus 2. So they will have another energy, and M equal to 0, 1, they will have another energy. Okay, so if you don't consider the electron hopping, then this dz square will have the lowest energy. Okay, but of course the relative energy position will actually change if you consider the electron hopping. Later I'll show you to this. Okay, now let's consider the S atom. This sulfur atom, you can see that it is in this position in the periodic table. It occupies the p orbit. I mean, the outermost electron occupy the p orbit, and there are 2 more. You need to fill 2 more electrons to reach this argon complete shell configuration. Okay, and you have MoS2. So 1 MO atom corresponds to 2 sulfur atoms, and each sulfur atom needs 2 more electrons to reach the fully shell. So totally, MO atom need to contribute 4 electrons. Okay, so each S atom needs 2 electrons to reach the fully filled argon configuration. So 4 electrons in the MO atom will form bonds with the S atom. I mean, they will contribute, but those electrons, they don't completely just go to the S atom. They just form a bond. So it's form a bond, form the bond. Then there will be 2 electrons remain. Totally, you have 6 electrons in the MO atom, and 4 of them will form the bond with the S atom, and then 2 electrons will remain. And those 2 electrons will be relevant for our band structure. Is that okay? So if you have 2 electrons left, then where will these 2 electrons go? So from the relative energy position here, you know that they will just go to the dz square orbit. Okay, so if you just have an atom without considering any hopping, then the ground state configuration will be the dz square. So it's M equal to 0. Okay, any questions? Okay, so let's move on. So now we need to consider the electron hopping. The electron hopping. Because this electron does not just stay in the MO atom and they don't move. At the gamma point of the band structure electron, they don't have the momentum. Okay, but generally, the electron will hop. And this hopping in the time binding model usually just a hopping between the MO atom. Of course, it can be mediated by the S atom, but it will be hop because they're d orbit. Okay, the d orbit will hop to the d orbit of the other atom. Okay, so it's a hopping between the MO atom. It's not like graphene. Graphene, the time binding is hop from A side to B side to B side to A side like that. But this is a hopping from MO atom to MO atom. But it can be mediated by the S atom. Okay. So when the electron hops across the lattice, the different d orbitals, they will mix. They will mix to form the one-near state. They will mix to form the one-near state. So, okay, let's consider the mixing. First, we need to know that there are mirror reflection symmetry. Okay, they're mirror, because if you change z to minus z, they will be the same. And if you consider this orbit, you can already see that if you change the z sign, this silver one will become red one. So that means the sign of the wave function will change if you apply the mirror symmetry operation. So that means this m equal to plus or minus 1 has odd parity. Okay, but if you look at here, m equal to plus or minus 2, if you flip the sign of z, they will just be the same. So this set has an even parity. Okay, even parity. When you look at the dz square, is the same, is also even parity. Okay, so you need to know when MO atom is in this trigonal prism, all the effect of the S atom has the mirror reflection symmetry. So that means if these two of them has different parity, they're not going to mix together. Not going to mix together. So this one, odd parity, these two will not mix with the others because they have odd parity, and the other two sets they have even parity. Okay, but these two will mix together. These two will mix together because they have the same parity. Because the effect you apply on it has the mirror symmetry, so different parity, they won't mix together. Is that okay? Okay, so this is the band structure of monolayer MoS2 calculated by first principle. So in this band structure, they use the size of the dot to represent the contribution from different orbits. So let's look at dz squared. Dz squared. So this red open dot are the dz squared. So you can see that the dz squared dominates the contribution at the gamma point. Okay, this is what I showed before, right? Because at zero momentum without hopping, the dz orbit is the lowest energy. Okay, so at the gamma point here, the conduction band on top, you have the blue and green, and they correspond to these four orbits. Okay, and then the valence band has the dz squared. Okay, so this is when you don't have the hopping. Okay, but once you have the hopping, they will mix together. They will mix together, and then you change. So when you go to the K point, then you can see that the dz orbit, the conduction band actually will be contributed mainly by the dz square orbits. Okay, you see these are open red dots here. They're the dominant one, and the valence band is contributed by the dxy and dx squared minus y squared. Okay, so these are mainly the blue dots. Okay, and you can see that the green dots are this dxy and dyz. So they are the m equal to plus and minus 1 orbits. They have odd parity. So you can see that the green dot they don't overlap with the other two color. You can see that the red one and the blue one, they mix together, right? They mix together. But the green one, they are decoupled because they have odd parity. So they are decoupled. Okay, so this helps us to simplify the situation. So the blue and red bands here, they have even parity, they mix together, and the green lines, they have odd parity and they don't mix. So that means in the calculation of the band structure, we don't need to consider the green one. We only need to consider the red one and the blue one. So that means this dz squared and dxy, dx squared minus y squared. So this simplifies the situation by just using the symmetry consideration. Okay. So we're going to construct a minimal model to calculate the band structure near the K and K prime points. So you look at this band structure. If you near the K and K prime points, you can see that in the conduction band is mainly contributed by the dz square. Okay, the dz square. So we're going to use the dz square as a basis function as a basis. And then on here, on the valence band, is mainly contributed by dxy and dx squared minus y squared. So we're going to use it as a basis. But we're going to use a combination of it. So generally, if you want to calculate this whole band, you need to consider each of these three orbits separately. You're going to have three bases. Okay, three basis function. So if you do the time binding model, you're going to have a 3×3 Hamiltonian. Okay. However, if you only consider at the K point here, then you can simplify it. You can make a linear combination of dxy and dx squared minus y squared. You make a linear combination like this to reduce it into only one function. So why can we do it? That was because at the K point, there's a C3 threefold rotational symmetry. Okay. Oh, the K point has that. Okay. Only in high symmetry point, you have rotational symmetry. In K point, gamma point, you have rotational symmetry. So once you have, in the K point, you have threefold rotational symmetry, then you know that the M is a good eigen number. because m is the quantum number for the rotational motion. Okay, when your atom has rotational motion or rotational symmetry, you can know that m is a good quantum number. So at the k point, you have threefold rotational symmetry. You know that the m is a good quantum number. So you're going to construct this. So what is this? This dx squared minus y squared, this one is just the combination for the m. Okay, so I have shown you before, right? This combination will give you m plus 1. And this tau equal to plus 1 and minus 1 is for the two values, because the two values they're connected by time reversal symmetry. If in one value you rotate in this way, on the other value you rotate it in the opposite way. So that means for one value you have m equal to plus 2. Then for the other value you have m minus 2. So the corresponding band will be the eigenfunction of the m. Okay, so for the valence band, you have a basis function in this form. On the conduction band, you have this form. So you have two bases. Then you're going to use these two bases to construct a Hamiltonian. And then let me show you the result. From these two functions, you can construct an effective Hamiltonian in this form. Is the same as in graphene, but the interpretation will be somewhat different. Okay, so I'm going to show you how to derive this Hamiltonian from these two bases. Do you have any questions before I start? Okay, so then I'll start. So I'll start to derive it. First, I will start from the. We're going to use something called the KP approximation. KP approximation. So let's write down the Schrodinger equation for the crystal. So this is the Hamiltonian of the whole wave function. So you're going to have nk. ENK. So n is the band index. We're going to use n equal to C of V. Denotes. Because in this derivation, we only consider two bands. Okay, in the simple case, conduction band and valence band. Okay, so we're going to do the expansion near the K point. Okay, near the K point. So we're going to write this one. By the way, have you learned the KP approximation before? Do you? Okay, it's okay. I mean, I didn't learn it when I learned solid state, so that's fine. I'll just do it from the beginning. Okay, so you know that this one has a form like this. Okay, so this is the block state, and then including the plane wave. Okay, you learned this in solid state physics. But right now we're considering the state at the K or K prime value. So we want to do the expansion at the K point. So we're going to consider this is for general K, for general K. So we are going to consider K equal to near the near the K point. This is a big K point on plus minus near the K prime. People just usually use a big K points. So we'll just you can write it in this way. You use plus K vector minus K vector. Either way is okay. It's K or K prime or plus or minus K. But when you use plus or minus K, you really mean the vector. When you use K and K prime, it's not a vector. It's just the name of that particular point, like gamma point, M point, K point. They're not vector, okay? They're the name of the points. But when you say plus or minus K, they are vectors, okay? So we use tau equal to plus as the Valley index, okay? So K will become plus or minus tau. No, not plus or minus. Tau K plus K. So here, this K represents the not momentum, is wave vector. Represent the from the K point. From K points. Okay, so this K is not a general K. It just you count it from the K or K prime points. Okay, so how do we do the expansion? So we use this. We use this one, copy. Then we're going to write it in this way. We're going to write it in this way. Okay. And cost this one. Okay, so then we're going to this is dot R. We're going to take this part out. And then copy this. Okay, so we're going to name this. We're going to name this as NK. Sorry, there's an N here. There's an N here. There's an N. Okay, the band index. There's an N here. Okay, so we're going to name it. We're going to add the tau here. Okay, add the tau here, just to represent this wave function. Okay, so basically with this will just equal to this. Okay, so because this K is the K is small, the K is small, so we're going to do the expansion on it. Okay, so now let's go back to this original equation. Sorry, I forgot the wave function here. There's a wave function here. Okay. Okay, so this one will become copy. And then I'll take this expression, put it here. Copy. Okay. Okay, good. Then we're going to apply on it. So what is P? So we don't need to worry about the potential here. The main operator here is P. P is H bar over I gradient. Okay. So basically P square means you're going to have negative H bar square and then square. So what does it mean? Basically, it means you're going to use this do two derivative. Okay, so let's not worry about this part. Let's only worry about this operator. When you have 2i means you have summation over x, y, z. Okay, so let's consider this part. Okay. So let's consider copy. Let's consider this part. Okay, so how will this change? So first you apply the product rule, differentiation. So once you do this derivative on here, you're going to bring down the I component, the Ki component. Okay, so I'll skip this R here. Okay, just to make it simple. Then another one will be U. Okay, so this is one derivative. Okay, then you're going to do the derivative one more. You just apply you apply one more time. Okay. And then you apply again on the other side. So okay, so this is the first line. Then for this one, then you're going to do it like this, Ki, and then U tau and K. And then you're going to do this on here. Then you have NK. I mean, all of these K, they're vectors. Okay. Get the vector here. Okay, they're all vectors. Okay, so you will see that these two are the same. These two are the same. So just let me write it one more time. So what is this? This you need to sum over this I. This is complex imaginary number. These are the x, y, z. Okay. So if you sum them together, I give you -1. Then you have a k vector square. Okay. Then you have this. then this one eventually you have a 2 here. You have a 2. You have a 2. And then this one will become a gradient. Gradient. Okay. So if you consider all of it. Okay. So this one, this will be gradient square. By the way, this is not just gradient. You have the I and this one. So you'll be K dot gradient. Okay, will be the K dot gradient. So you have 2I K dot gradient. Okay, so okay, so you can actually group them together because all of them this one plus 2I K dot gradient plus gradient square. You have UN this, and then the phase factor is just a multiplication. You can put it here. Now, so far we haven't made any approximation. We just rewrite the equation. Okay, so so you need to know that this. So here, gradient is just I omega p, right? Okay, so double gradient is negative HP square. I mean, this is the correspondence. Okay. Okay. So now this equal to negative K square. This gradient here. I just copy. And then this dot thing. Okay. Then the gradient will be this copy. Is the minus sign is already here. Okay. So okay. So now let's rewrite this equation. Let's rewrite this equation. This equation will become so this term is basically this term. Copy this term. Of course, you have the. Let me see you. Here I only consider this. You need this thing. Copy. It looks like a redundant. I add this thing and then copy this. Okay, you need to add this factor here. You need to add this. You need to add this factor here. Okay. Okay, you need to add this factor, and then yeah, and then plus V EI and then plus this. Okay. Okay, so you just rewrite in this way. Now the key thing here is that you can cancel this factor. Okay, this is the key thing. Okay, when you do this kind of operation, you can make this factor come out and they get canceled. Okay, after you cancel it, then this term will just become P squared 2M. Then this term will become, let me see, I will be minus, you have a minus got cancelled. So you have K, you have K dot P. Yeah. K dot P. And then let me see, you have the 2M and then a 2 here get cancelled. And then you have a M here. So this is H bar squared, this is H bar, so you still have 1 H bar. So let me H bar here. Okay. Then you have this term with this term. So you will be K squared over 2M. Okay. Then you have, then you add the VR here. Okay. You add the VR here. Then after you cancel, you only have this part of the block function. Okay. Then you have the energy. Need some space. Yeah. Okay. Okay. So now you arrive at this equation. This equation. Now, so far, there's no approximation. You just rewrite the Schrodinger equation into a form that you are solving for this block function without the plane wave. And what is this? This is the wave function at the K or K prime points. Okay. But it has this momentum counted from the K or K prime points. Okay. But the energy is the same. So we want to solve it for the energy, right? When you have the energy, they have the dispersion, right? So there's no approximation so far. So far, there's no approximation. The equation is exact. Is exact. Okay, now we're going to make 2 approximations. Okay. Okay. We will make 2 approximations. First, we will consider only 2 bands. N equal to C and V. So once you make 2 bands, that is a significant cut of the wave function. This is actually a set of equations. It's a set of equations because you have an N index here. That means you go through all the different bands. And this part, is going to mix the bands with different ends. This KP, K dot P part, this is a derivative. Okay, this is a derivative. P is a derivative. Once you do a derivative on the wave function, the outcome will be a mixture of all the bases. You get it? Okay, so it will mix. So if you say I'm going to cut all the other band, I only consider 2 bands, then a whole set, infinite number of equations now only become 2. You only consider mixing between 2 bands. Okay, so this is the usual approximation for the KP approximation. Like you consider all of these terms, but you just cut out all the bands and only consider 2 bands. And this approximation is only good when the other bands are far away. Like you have 2 bands here, okay, and then the other band are here, they're far away. So the mixing effect will be small. So these 2 bands will mix the most. So that is the reason that you can use the approximation. But can we justify this in our case? Then you just look at the calculation here. Now you need to know these green bands, they decouple. They're close, but due to this different parity, they don't mix. So they're not relevant. Okay, they don't mix. Then you have this red and blue bands, they're mixed, and the green band, they are not mixed. And then all the other bands, I mean, at least from here, you just don't see. You just don't see them. I mean, if you have another band mixing, it will be up there, okay, or down there. You just at the K point, you just don't see other bands that can mix. Okay, they will be not close. Okay, so this justifies why you can use the 2 band approximation. Is that okay? Okay, so the second approximation is we only consider small k. That means you only consider the band edge. So we'll neglect the k squared term. Okay, so these are the other 2 approximations. So this one we already justify that the other bands are not close. This one, as long as you are close to the band edge, then this is also good. And for the optical measurement, you are basically considering the transition near the K points. Because let's say for PL, then all the cables will relax to the band edge. Okay, so it's relevant to our research. Okay, so these are the two approximation. Okay, so once you understand this, then we're going to continue. So the equation will become then you can neglect this. Okay. And you're going to have 2 equations. You're going to have 2 equations. Let me see. Copy. You're going to have an N. This is for C. This is for C. And this is for V. Okay. So these are the 2 equations. Okay, we're going to name this as H K. Okay, and you're going to have a tau here to denote that it will actually be different when you have different tau. Okay, it will actually be different. Although there's no tau inside, later you'll find that it would actually depend on tau. I'll leave the tau out for now. Okay, but later we are going to show that it will be different. So we're going to name this as H0, the original Hamiltonian, and this one we just call it H prime. Okay, that means it's a perturbation, Okay. Okay, so we are going to solve this. We're going to solve this too. So let's consider the basis. So we will use U tau C0 and U tau V0 as the basis, as the basis function, Only two. So you're going to get a 2x2 matrix for the Hamiltonian. So what are actually these two functions? How is that related to what we derive here? Okay, so we derive it here, but they're not exactly the same thing, because U C0 is a function of R. So this will be a block state at the k points, or minus k points. So what is the form of the wave function? So let's understand this basis function. It will be this function C. Okay, so will be this function C. Okay, and then it will depend on the site. Okay, then you're going to have I tau k dot the site, and then you're going to sum over all the site, and then you will have a normalization factor of n. So this is a one-near state. This is the localized. This is the atomic orbit. The orbital, and we know that it is dz square. Okay, we know that it's dz square at the R site. So for each site of the atom, you have the dz square orbital, but you're going to sum over it over all the sites. Okay, and you carry this plane wave phase factor, and then you can construct a one-near wave function. Is it okay? I mean, we use the same trick for graphene, right? Okay, so similarly, copy for the V, V. So also for the C. And this one we actually depend on tau. It will actually depend on tau, because it depends on which part it is. Okay, so this one is the atomic orbital. You have the D, what's it? X square minus Y square, and then plus I tau dxy at the site. Okay, is it correct? Okay, that's good. Okay. Okay, so these two are the bases. These two are the bases. These two are the bases. So we're going to express this. So 0 means is exactly at the k point. The small k is 0. Okay, so let's look at these two. Copy. So each of this will be a linear combination of these two. Copy. Will be a linear combination. So I'm going to use a coefficient A and B to represent them. Okay, so you're going to expand this wave function that we want to get into a linear combination of the two functions that we already know. These two are known. Okay, we know what they are. We know what they are. We know the atomic orbit, and we know that by using this construction, you get these two. Okay, these two are known. These two are not known. This is what we want to get. Okay, so then copy. And then here, the coefficient will be different. So I add the prime here, A prime, B prime, to differentiate them. Okay. So basically, our goal is to obtain A and B. Once you know A and B, A prime and B prime, you solve the problem. Okay. Okay, so now let's apply this whole thing. Okay. HK and on U. Okay. And then let me see. So let me use this part. Okay, so take this one, apply on the Hamiltonian, and then take this one. Let me. Okay, because I didn't bring my note, so I have to do it on site. Okay, I think it will be slower, but let's do it together. So I'm going to take this. Take this, copy. Plus, let me just write this out. Just take this part. Copy. Okay. Okay, so it will be like this. And then we're going to take the product on this part. Okay, so let me take this. Remove the I. Remove the I. Okay. So copy. Okay, so Let's deal with this part first. So what is this? This is just E. Just ECK tau. Okay, because this is Hamiltonian, the actual Hamiltonian. Okay, so this is the actual Hamiltonian. So what about this one? This one, then you're going to use the expansion. You're going to use this. Okay. Then you need to expand it. You need to expand it. There are totally 6 terms, 4 terms. You have 2 here, 2 here. So you're going to expand it. So let's write them out one by one. C0, H0, and then U tau C0. So this will be one term, will be A. And then you have a B term, H0, U tau V0. Okay, second term. And then you have A, H bar, K dot P. U tau Z0. And then you have B, U tau Z0. Okay, 4 terms. 4 terms. Let's consider them one by one. Let's consider them one by one. First, this term, what is this? This is the Hamiltonian, the original Hamiltonian at the K point. Because this one is this thing when the K is 0. Okay, and when the K is 0. So when this apply on this at K equal to 0, you just get the energy. You just get the energy. So what is this energy? This is just the energy of the conduction band at the K point. Is that okay? And we just set it to be delta over 2, half of the band gap. Delta means band gap. The size of the band gap. It's a conduction band, it's just half of the band gap. And what is this? This is 0, because this one is the eigenstate of H0. And this is the conduction band. So valence band and conduction band, they are orthogonal, right? So you can, this one is just 1/2 of the gap. So it will be negative this B. So this is 0. Because these 2 bands, they are orthogonal to each other. Okay. Okay, now let me see. Okay, this part. So this you can take it out. A K dot. So this one is the permanent dipole of UC. I mean, you're taking the same wave function and get the expectation value of the dipole, right? And it is 0. It is 0. Why it is 0? Because this system has a threefold rotational symmetry. Okay. So for example, let me give you an example. If you are in an atom with the inversion symmetry, you know all the atomic orbits of the atom, they have no permanent dipole. Do you know why? Okay, let's say you consider hydrogen atom, the p orbit, s orbit, d orbit, none of them has a permanent dipole. Do you know why? Huh? Yeah, because symmetric. Because for atom, let's say for atom, these two have the same parity, no matter even or odd. They have the same parity. They have the same parity, and this one have odd parity in an atom. So when you have odd parity, same parity, you do the integration, you always get 0. Because this is a number. The only number that has odd parity is 0. Like you flip the sign, is the same. Because number cannot change, it's just a number. So you flip the sign, is the same, is always 0. And the same for threefold rotational symmetry. So if you have threefold rotational symmetry, if you have because the wave function rotates for 120 degrees, it stays the same. Okay, but the permanent dipole is there, right? If you rotate the permanent dipole for 120 degrees, it becomes another dipole. But that permanent dipole is unique, right? You have a system there. If it has a permanent dipole, the dipole just stay there. You rotate 120 degrees, the system already rotates. But after rotation, the system is exactly the same as before. But your dipole cannot be the same because the dipole will have to rotate together. So you don't. So that permanent dipole, the only permanent dipole that can remain the same after threefold rotational symmetry is 0. Okay, if you have a finite dipole, after rotation, it will become another dipole. It cannot be the same. So that means you have the same system, but you have more than one outcome. That's logically, that's not possible. The only possible solution is that dipole is 0. Okay. So these two can rotate. So this is 0. Do you understand the argument? Yes, threefold rotational symmetry. The eigenstate will have 0 permanent dipole. Is that okay? Okay, so this is also 0. This is 0 due to the 3-3 rotational symmetry. Then what about the z direction? Because you consider xy has rotation. What about the z? You have C3 rotational symmetry in the xy plane. It doesn't mean that your z component will be the same, will be 0. Then in this case, you use the mirror symmetry. In the z plus z and minus z, you flip. Then you use this parity argument. You apply the mirror symmetry. These two, because they're the same wave function, so they have the same parity. And this p dipole has the odd parity, so it's also the same. So by using C3, threefold rotational symmetry, threefold rotational symmetry, and the mirror symmetry, C3, and the mirror reflection symmetry. So it's the same. Okay, so that's a good simplification. Then for this one, Then you have the B. This one is not 0. Okay. So why is this one not 0? What is this? What is this? This is a V to C with the dipole. This is just the transition dipole from the valence band to conduction band. It would not be 0. If it is 0, then you don't see any optical signal. So it will be finite. It is finite. This is the transition dipole between the C and V band. It is not 0. Okay, it is not 0. Okay, very good. So we have simplification. So so we just copy this. Then on one side, you have copy this. On the other side, you have all this big chunk of stuff. Let me copy it. Okay, you have this whole big chunk of stuff. Then delete. Delete this. These are 0, 0. So 0. This is also 0. So this is delta over 2. Okay, so this is A times delta over 2 plus this. And what is this? This thing is this part, right? So you copy this. Copy this. Huh? Then this take the linear combination. This one will go away. It's orthogonal. So eventually, you just equal to A. I mean, just do a projection. You get an A, right? Okay. So eventually, you get just this times A. Is it okay? Okay, now, okay, it's a bit tedious, but we have to do it one more time. Now we do exactly the same thing and project into another state. This one will be faster, okay? So because now we take the projection on conduction band, right? So now let's do it one more time. On the valence band. On the valence band. Okay. So this part, very quickly, this becomes E. This will become EV K. Sorry, it's still EC. EC, sorry, still EC. And then you you move the ECK outside. So you're doing the projection on V. That means you're going to get this part. All right, let me quickly copy this then. Okay. So you're getting the projection on V. So this will be 0. You're going to get a B. So this will give you a B. Okay. Okay, we solve it for one part. Okay, then for another part, you basically do the same thing. This one will equal to this one will be this. Copy. Okay, then you're going to expand it. You're going to expand it. Then you're going to get 4 terms. Then let me copy and paste. Okay, so we're going to get 4 terms. Copy. Not enough space. Let me compress this a little bit. Okay. Okay. Move it here. Huh? What happened? Sorry for the mistake. Okay. Let me copy and paste one more time. Okay, this one. Okay, so this one will become like this. This one. Okay, good. I think now it will work. Okay, so now all we need to do is to change this C into V. Okay, we're going to change this into C. Sorry, V. Okay, after you change it, then this one will be 0. So I'm going to move this to here. Move this to here. Okay, so this is the advantage of using copy and paste. Okay, this will be V0, C0. Okay, so they are orthogonal to each other. Okay, they are orthogonal to each other. In this case, actually, the energy is still is this. Okay, is this. Okay, the second term. What is this? So this is the energy of the valence band, because both of these are valence band. So we set the valence band to be half of the band gap minus half of the band gap. Okay. Then, okay, now this is the valence band, and then dipole moment. Okay. This will be the dipole moment. V0. So the valence band has no dipole moment. So this one will be 0. Okay. Move this out. Okay. So this one will be 0. Okay, this argument move to here. This 0 due to the threefold rotational symmetry. So this is the permanent dipole of V0. Okay, so this is 0. And this one is not 0. So this one is the transition dipole. So this transition dipole now is from conduction band to valence band. It's an emission. It's an emission. Okay. So it's not 0. Okay. So then eventually you have an equation. Yeah. Prime. Okay. And then will be A dot now plus sigma B. Okay. So now let's combine. So this is the first equation. So we combine them together. Is that negative? Yeah, negative. Okay. Yeah, fine. Okay. Thank you for the correction. No, not prime. Not prime. They're not prime. Because we only change this part. We only change this part. This part has not changed. This part has not changed. We're always just conduction band on one end. This part is valence band and conduction band. So is they're all A. Is that okay? Okay, so we combine together. Now we're almost there. We combine the two equations. So we get something like this. Okay, so we are going to make it a matrix form. So you're going to get E, C, K, and then A and B. And then this one, we're going to make it a matrix. A and B. So what is A? This is delta 2. This is negative delta 2. Okay, we're getting there. So B is H bar over MK dot and then H bar over MK dot U V0. Okay, so you're going to do the same thing. I mean, I'm not going to repeat it. Okay, I think it will be too tedious to repeat it. You're going to do exactly the same thing and put this into here. Okay, so when you expand this one can be conduction band and valence band. This one can be conduction band and valence band. This one always with a small k. So you're going to use either this expansion or the other expansion. This one can be conduction band and valence band, but it is always 0. So after you do the projection, I mean, so far we have done this, right? We use the first equation, put it in, and then make the projection on this one or this one. So we get the 2x2 matrix, right? So you're going to do the same thing. Maybe I'll leave it as an exercise for you. I think it's good that you go through it once by yourself. So maybe when you go home, you do the expansion on this equation. The result is exactly the same. So after you do this, after we do it again with the U tau VK. So we have done C, right? We'll get the same thing. I mean, I actually haven't done it by myself yet. Maybe it's wrong. You go and confirm it, but I think it will be the case. According to my feeling. Okay. So you get something like this. This will be V, and then of course you have the prime for all of them. Okay, but the Hamiltonian will be the same. The Hamiltonian will be the same. So basically what it means is that you have one Hamiltonian. It has two eigenvector, one eigenvector, two eigenvector. Then they correspond to the two eigenvalues. That's it. Okay. So this Hamiltonian is just the HK Hamiltonian. Tau. With the K, with the two band K dot P approximation. You can call it the K dot P. Of course, to the K order, because we neglect the K square. If you include the K square, you'll get a more complicated like one, but it's still 2 by 2. Now the two band determines that this matrix will be 2 by 2. The K dot P, you can see that this is the K dot P, right? If you have a K square, then you have the more things. Okay, this is this Hamiltonian here. You can already see that it depends on the value. If you change the value, it will be different. Okay, but what is the difference between this K, this HK, and the other one? Originally, we also said this one, right? So what is the difference between this one and the one that I show you? There's a difference. This one, let me see. Oh, they're actually the same. They're actually the same because here I already used the two band. I already make the K dot P approximation. So they're actually the same thing, a different representation. This is a representation using a set of equation. And on the basis, on the wave function of this one. The other one is you use this basis. You need to know that equation that we derive is to get A and B, A prime and B prime. Okay, so basically it's the same Hamiltonian expressed in two different bases. On here, it is expressed just directly on these two functions. Okay, over there, you just solve it. You just solve it to get A and B, A and B. So that's the same Hamiltonian on two different bases. On that basis, use that equation. On this basis, you use this Hamiltonian. But this Hamiltonian is good because it shows, later I will show that it will show a form of the Dirac equation. But from here, you still don't see that it is a Dirac equation because Dirac equation is K dot sigma. But this is not sigma. How are we going to change it into sigma? Okay, so we're going to continue to derive it. Then I think we're done after that. So this one and this one, they're just complex conjugate with each other. You can see that this is V to C, this is C to V. Okay, so we're going to deal with this to make it into the sigma thing. Okay, so let's deal with it. Okay, so we are going to use an operator called I call it P plus and minus. Is Px plus and minus P should be a small p. Okay, a small p because it is a Px plus and minus Py. So this corresponds to a circular polarization. Okay, so after that, what is Px? So Px equal to P plus P minus, and then 1/2. Okay, so Py is P plus minus P minus. After you minus P minus, you get the 2i. Okay, you over 2i. Over 2i. Okay, these are simple math. But 1 over I is just negative 2i. 2i. P plus P. Okay, so let's. So sorry, 1/2. 1/2 negative I. Okay. I want to write it out so that you have a negative I. I mean, here you already see this is 1, this is negative I, so you're already getting the impression that the Pauli matrices are going to come out. Okay. So this is Px x Py and then you are going to separate them. You're going to separate them. Do we? Let me see. No, because your K dot P, your K only has the XY component. The Z component won't be there. Yeah. In this model. Py. Okay. So you're going to separate them. Let me see. You're going to write 4 terms. P plus X P minus, and then P plus. This will be minus. This minus sign is actually important. It is actually important. Okay, let me highlight it. P minus. Okay, so they need to leave some space. Okay, let's consider them one by one. I just use some symmetry argument to maybe just use angular momentum. I can quickly rule out the sum of the terms as 0. Okay, so let's do it one by one. Okay, this one, this V. This, what is that? This is just M equal to M equal to 2 tau. This is a Valley index, right? So when tau is +1, this will be 2. When tau is -1, will be -2. Okay, so it has an angular momentum. Angular momentum. Angular momentum. M this. Okay. So this one has a M equal to 0. Okay, though this is a photon with a spin 1. Okay, a photon spin +1. Okay, so there's a check here. Okay, I need to, if you learn group theory, it will be a little bit easier to understand. So you consider the transition. So let's say this is M plus 2 first. This is M minus 0. In principle, you won't be able to make the transition because no one photon will be able to connect these two. However, there's a threefold rotational symmetry. Okay, that is important because this angular momentum will become crystal angular momentum. So you know what momentum means, right? So momentum conservation is this. Okay, let me momentum conservation. You have a P equal to P1 plus P2. Okay, this is, but you have a crystal. You know what crystal momentum is, right? Crystal momentum means this P equal to P plus any of the reciprocal lattice. I think you have a H bar. Like all these different P, they are the same thing. Okay, so it's because it's a discrete translational symmetry, not continuous. Okay, so crystal momentum and momentum, they are usually the same, but once you consider conservation, then crystal momentum has this. Okay, all of them are the same. So for crystal momentum conservation, this P can be P1 plus P2 plus a reciprocal lattice. Okay. So what about angular momentum? I mean, I talked about this before. I mean, let's review it. So normally, I mean, you need a J, okay? J equal to J1 plus J2. But for, I mean, I didn't really see the term crystal angular momentum. I don't see this in the textbook, but the same principle. So here, plus what? Plus 3 times n. 3 means threefold rotational symmetry. So that means everything is once you go to 3, it becomes 0. Like you have 0, h bar, 2h bar, 3h bar, 4h bar, 5h bar. But because it's threefold rotational symmetry, so that rotation is you make it 3 times, you go back to the same. So this one will become 0, h bar, 2h bar again. So 0 and 3h bar, they correspond to the same state. Is that okay? Similarly, when you have negative h bar, negative h bar, negative 3h bar, then this will be 0, 1h bar, 2h bar. So what does it mean? That means when you consider 0 here, what is this? This is just negative h bar. This is negative 2h bar. Because these are they're just the same state. The same state. Okay? Did you get it? Okay, so when you go back to here, this is let me consider if tau is 1, like k value, then m is 2. What is 2? 2 is just negative 1. Okay, 2 is just negative 1. So you have a negative 1, you have a plus 1, then you can become m0. So this term will be finite for tau equal to plus 1, and will be 0 for tau equal to negative 1. Do you get it? If it is negative 1, then m will be negative 2, will be what? Negative 2 is what? Negative 2 is just 1. Okay, so you have 1h bar plus 1, you won't get 0. So this transition is forbidden. Basically, just the value selection rule. Okay, so this term is finite. Okay, so we quickly go to the other term. This one is the same as this one, but you have this become negative. So this spin is negative. This one will be what? M will still be 2 pi. This is m equal to 0. So then you can already know that this will be what? Will be 0 for tau equal to plus 1. Will be finite for tau equal to minus 1. Is that okay? And you get exactly the same thing here. This one is exactly the same. I mean, this one exactly the same. Okay, exactly the same. This one is also exactly the same. Okay. So let's define. E CV how can I differentiate plus or minus? Okay. Just use PCV then. It already means chiral. Okay. Let's define this. P plus. It will be plus 1. Plus 1. Okay. because this is means as this. This is finite. So if you apply time reversal operation on it. So you have time reversal operation on PCV. PCV is just a dipole, is a number because it's only a component. It's a number. When you apply time reversal symmetry on the number, you just get the same thing. Okay. So this one, however, if you apply time reversal symmetry on here, then you need to apply it on all the states and operator inside. So this one will become U minus 1. You flip the value because time reversal symmetry. This one will flip. It become minus. And these are U. They're all U. So U. So this will be minus V0. So this one is still PCV. Okay, so that means, so what is this? So that means so that means this whole thing will become 1/2 PCV. This is PCV, right? And then let me see. Plus 1 is PCV. If you get minus 1, you get minus 1, you get this. It's still the same thing. Okay. For the X component, no matter which value you get, either this term or this term, because these two things, they are the same when they are finite. Is that okay? Like we already proved that this and this, they're the same. They're the same value. Okay. And here, no matter each value you are in, you get plus 1 value, you get this. You get minus 1 value, you get this. You get the same thing. It's okay. So you will be just X. Okay. However, for Y, if you get plus value, you get this term. You get minus value, you get this term. However, there's a sign here. This sign is important. You are going to get opposite in Y. So that means you are going to get, you're going to get a tau here. When it's minus, you're going to get this term. You're going to pick up this minus sign. So I just use a tau. Tau is minus. So this will be like this. Can you follow? Yeah. Okay. PCV. Okay. Okay. So where are we? Okay, so well, let's go back. Okay. So we're going to copy. Okay, so we're going to write this. This is H bar K. We're going to get this thing. Let me write in a better way. 1/2 PCV X plus minus tau. Okay, so that is what we get. Let's take away this minus. Copy. And then you're gonna get this. This one is just the complex conjugate of this, because the Hamiltonian must be Hermitian. Okay, you just flip the Bragg and cat, so you get you get a complex conjugate, so you get the same thing. And then here you must flip the sign. Okay, you must flip the sign. This one can stay the same, because you can, I mean, in principle, you should add the complex conjugate here. But I think it is a real number. I think it is a real number. Yeah. If you do a more detailed calculation, I think you'll get the real number. Okay, so and you can do it if you want to challenge. You can try to do it. Okay, so you just get the same. Yeah. So okay, so get A and B. So yeah. So PCV. Let me get PCV equal to is real number. Okay, so now let me see how we're going to deal with it. Okay, so now we get H bar M 2M PCV K this dot this is KX KX, and then what minus I tau KY. Okay. Plus so, and then we're going to separate this. So the Hamiltonian K equal to this. So this X part is just KX is just 110. Okay. So KY part, you have a tau here. You'll be negative I. Then you have delta 2, 1, negative 1. Okay, so the Pauli matrices just come out. Okay, so what is this? This is just sigma X. This is just sigma Y. Sigma Z. So these are the Pauli matrices. So you can group them together. PCV. You have KX sigma X plus tau KY sigma Y. Okay, so this is the direct equation. Okay, so now you can actually make a coordinate transformation. Coordinate. initially you have X and Y. You can change it into X and Y. Just rotate for 90 degrees. So in this case, X will become negative Y. Y will become X. But the net effect is this. K dot P KY PY will become negative KX. Let me see. This will X will become Y, right? So you have KY, KY. Sorry, negative KY. Then you have negative PY. And then KY here will just become KX. And then this will become just PX. So basically you just get the same thing. Okay, so then you look, it's a bit trivial. Okay, what do you mean? So basically you can flip X and Y. Okay, because both of them carry the same sign. However, you flip the X and Y here, this tau is going to go to the other side. So this Hamiltonian, the tau will go to the other side. Hamiltonian will be this tau is going to be here. Yeah, you can actually follow. Okay, basically you flip every X and Y. I haven't done it by myself yet. But if you want, you can use a new coordinate and just go through the steps. Because everything just happened. Follow the X and Y here. Okay, so if you flip the sign, this X is going to become Y. Then this Y thing will become X. Then this negative sign here will go to the X side. Okay, then because the value index comes from this side, there's a negative sign here. Okay, so eventually you get a Hamiltonian like this, and this looks exactly the same as in graphene. Okay, and you can set this equal to AT. I want to make connection. Probably I don't need to make this connection now, because when you do the calculation of PCV in a time binding model, you're going to relay this. Related to the Hoping strength in a time binding model. I mean, we have not used a time binding model. We're using a KP approximation. It's not time binding, but this parameter is the transition dipole. If you do the calculation of that matrix element based on the time binding model, you're going to relate it to the Hoping. So eventually you get something related to the Hoping. And if you read this PRL paper, okay, I mean, they go from here to here just quite quickly. Okay, so yeah, they introduced the 3 bands here, okay, which I show you in the PowerPoint, and then they define the basis, and then what they said is that to the first order in K, the C3 symmetry dictates that the 2-band KP Hamiltonian has this form. So basically, all I did in this long derivation is just one sentence. And then here, the sigma denote the Pauli matrices for the two bases. And then here, they just use A and T. A is the lattice constant, T is the effective Hoping integral. And this is the band gap. And here, because I did not use a time binding model, so I get the expression is somewhat different. But when you do the time binding model, you're going to relate them. So the Hamiltonian I got here is the same as here. So let me give me 5 more minutes. I'm going to add one more term here. So later they're going to add this spin-orbit coupling. That this term is very, very, very easy because this is a phenomenological term. You just add it there. Okay. So let me add the spin-orbit coupling because so far we have not considered the spin. There's no spin up or down in our consideration. Okay. So we're going to add the spin. So once you add the spin, you are going to get a 4 component. So this A and B here is going to become A spin up, A spin down, B spin up, B spin down. So of course we know that this is just the conduction band, the valence band. So this is conduction band up, conduction band, valence band up, valence band down. Okay, you're going to expand the wave function into 4 components by including the spin. So we have already learned the spin-orbit coupling, right? So in an atom, the spin-orbit coupling Hamiltonian is spin-orbit coupling is proportional to L dot S, right? So you go back to review our one of the previous lecture. We derived the form of a spin-orbit coupling from the Dirac equation. I gave 2 cases. One is for the Husbach spin-orbit coupling, Rashbach spin-orbit coupling under a vertical electric field, uniform electric field. The other is in the atom when you have a centrally symmetric electric field. For the centrally symmetric electric field, you will have a form like this. So this one can be written as proportional to LZSZ plus L plus this L minus. So it will be proportional to this. What does it mean? This means this is a spin conserved term on the z direction. Spin conserved term. So these are the spin flip terms. Basically here you flip the spin, lower down the spin, you increase the angular momentum of the orbit. Here you increase the spin and decrease the orbit angular momentum. So you can express this. This is a general form of this dot product. Okay. So in this system, if you neglect the spin flip term, like you consider that if you don't have the spin flip term, then the spin up and spin down, they're good eigenstates. Okay. Like the spin-orbit coupling will only contribute this term, and then it's a good eigenstate. But generally, spin up and down, like what I write here is not correct. Like the spin up state that if you consider rigorously, is not the eigenstate. You have your eigenstate will be a linear combination of spin up and down. Okay, so that's the general. But in this system, this term will be big. The other term will be somewhat small. Okay, will be somewhat small. This is because the other band with the opposite spin, they're far away. So we have a paper that talk about this. So if you want to learn more about this, you can go to our paper. So we have a paper. This very selective chirophonon replica of dixent trion. This is a paper that I wrote with Dr. Chang. So Erfu's work. So in this paper, I think we spend quite much time to write the supplementary material. So the supplementary material has a part on the group theory of exciton and chirophonon. If you go down, then it talk about the spin-orbit coupling, like this atomic orbit. I checked today, and the characters at different symmetry operation, and then the selection rule, and then once you have the spin, you're going to change the character, like all of this. Then basically the main idea is that if you don't have spin-orbit coupling, you're going to get a band like this. This is the model that I got today. Okay, once you have a spin conserving term, like the term that I show you here, once you include this term, you're going to get a band structure that with the spin up and down. But once you include the spin-orbit coupling, this spin up term and the other spin down term, they're going to mix together. The eigenstate will be a mixture of spin up and down, and that is the reason why the dark exciton can emit light. Okay, but this band is far away, like kind of far away. This is this band. It is far away. So I think this one let me see, it might be this band. Okay, that is quite far away, like more than a EV away, and the other one is also quite far away. Okay, so the spin mixing term is far away, so it's relatively weak. Okay, so that's why you can assume that this term dominates, so you have spin up and down. Okay, so once you have this, then this term for m equal to 0, this LZ AZ is going to equal to be m this, right? This z is going to be plus minus 1/2, right? So for m equal to 0, this will be 0. Okay, that's why the conduction band has no spin-orbit splitting in this approximation. It will have a small splitting because our model is so simple. You need to include all the other orbits, then you have a small splitting. So for m equal to plus and minus 2, then this one will be plus and minus 2. Will be finite. Will be finite. Will be in the order of what? H bar square. H bar square. Okay. So this is 0. This is H bar square. So we're going to add a phenomenological term that is spin up and spin down. They're going to be split. They're going to split. So here you have two cases. You have m equal to 2. You have spin up and down. The other one will flip. Let's say you equal to 2. Then it's pointing spin up. And then the negative spin will give you opposite sign. Then you have a spin up and spin down. So this we just call it the energy. Lambda. Okay, just call it lambda. The energy gap equal to lambda. Just like the delta represent the band gap. This lambda is just a phenomenological parameter. So we're going to add this term. We're going to add this term. Let me look at the paper. The paper uses sigma z minus 1 over 2. And then here they introduce a new Pauli matrix called AZ. So AZ is also Pauli matrix, but AZ is the Pauli matrix that applies only on the spin space. Like it only applies spin up and spin down. So you have sigma z and y and AZ. So here, AZ will apply on this one, and this one. This spin up, spin down. SZ apply on this two. Okay. The sigma Z will apply on this one and this one. So let me show you this. This sigma Z apply on this and this. Okay. And then the AZ apply on this and this. Okay, it's a bit complicated, but you get the idea. Okay, so what does this term mean? Okay, so for conduction band, sigma Z equal to 1, -1. Okay, for conduction band, you're taking the 1 here. Okay, for conduction band, you're taking the 1 here. You can say how spin orbit coupling. So then the 1 minus 1 will be 0. Okay, 1 minus 1 will be 0. For conduction band, this one equal to 0. Okay, for valence band, you're picking up a -1 here. Okay, -1 minus -1 will be -2. So it will be -1 minus -1. So this will be minus 1 and cancel this. Then this will be SZ. I think you have a valley index. You get at the valley index here. Here the tau. So then you add the tau here. So that means when you go to the opposite valley, you go to the opposite valley, then of course the energy will flip. Okay, because they're related to time reversal. Okay. But that is because here the SZ will have a -1. This will have a -1. So they actually cancel. You actually get the same separation. But just the spin is flipped. Okay, so eventually you get the Hamiltonian. Okay, so the Hamiltonian with K dot P and spin conserving spin orbit coupling. Full band is this how sigma Z minus 1/2 and SZ. Okay, so this is the result. This is the result of here. Okay. Actually, here is just 2 lambda is the spin splitting. Yeah, 2 lambda because here this is the energy. Okay, this is energy. You calculate as one spin is 1, the other spin is -1. So you take the difference is 2 lambda. Okay, so 2 lambda is the splitting. So after they get this Hamiltonian, what are they going to do? They're going to use this Hamiltonian and calculate the band structure and use that to fit the DFT result. Okay, you can have a DFT result with spin orbit coupling as well. Okay, so DFT is something like a black box. You input the material parameter, it just generates the band structure for you. You don't know, like the inside are a lot of numerical calculation. You just get the result. Okay. So, but it's difficult to do analytical calculation based on DFT result. Like you don't know what is the underlying selection rule, Berry curvature, all those things. You just see the band structure. So why do we need a Hamiltonian? When you have the Hamiltonian, you can use it to calculate the selection rule. You can use it to calculate Berry curvature. Like a lot of physical property can be obtained when you have the Hamiltonian, like conductivity, those things. So after you get the Hamiltonian, your Hamiltonian is going to have some parameter, like this parameter. You can treat this whole thing as just a parameter. I mean, you don't even know the effective mass. So you just treat the whole thing as a Hamiltonian. This band gap has a parameter. This spin orbit coupling has a parameter. So usually, so what people in that paper, they just relay this. They just relay this to and probably I don't need that anyway. They can just treat it as a parameter. So in that paper, they just take it as AT. A is the lattice constant. T is the hopping strength. Then they use it to fit this. They extract the parameter. So you can see this. This is the result that they fit. Okay, they fit it. They get an A. I don't know how they get the A. Probably they get the A for. Did the A just lattice constant? And then they extract the T from the DFT. Then they extract the lambda, and then they extract the band gap. And these are Berry curvature at the K points, K or K prime points. So that is basically what we did. The rest of the paper is to calculate the Berry curvature, which maybe I have the materials for that as well to talk about the Berry curvature. So basically, what I did today is to cover the first section of this paper. This is a paper that contains the basic physics for the MoS2, and the same model basically applied for the other TMDs as well. So they form the basis, and there are some I would say rich physics that can come out from the Hamiltonian. So finally, I know we are running out of time. I want to point out the difference between MoS2 and graphene, because I used to think that these two materials are the same, but actually there's a significant difference. For graphene, sorry, I'm running out of time, but for the sake of completion, let me comment on this before we end. For graphene, if you remember, the Hamiltonian of graphene is H bar tau, also Kx sigma x, Ky sigma y. This is the Hamiltonian of graphene. Okay, so we learned this already. I hope you remember. They are both Dirac equations. They are both Dirac equations. So for graphene and for MoS2, so basically you can copy this, the same thing for MoS2. For MoS2, monolayer MoS2. There's a big difference. For graphene, this is A atom. These are all A atom. Sorry. A. These are the B atom. So this Hamiltonian is applied on the A and B lattice. The wave function is A and B sublattices. On A and B sublattices. The hopping is this. You hope. So you hop from side to side. Okay. So these are the hopping. It's from A to B. Okay, if you apply different potential on A and B, like in boron nitride, you open the gap. Okay, so the band gap is due to the potential difference between A and B sites. Okay, you put it on boron nitride, somehow you break the A and B symmetry, then you open the band gap. So it's actually quite difficult to open the band gap with graphene because A and B sublattice is difficult to apply different potential. But for MoS2, is different. For MoS2, everything happens on the MO atom. The MO atom is here. Oh, sorry, I make a mistake. Yeah, here. Okay, so these are the S atom in our model is they're not participating. I mean, in reality, a small part is participating. That's why you have a small spin orbit coupling. That is due to the P orbit in the S atom, like partially. Because we only use a 2-band model, but there are more bands. They open a small gap in conduction band. That is not in our model. We did not capture that, but this is relatively small. So here the hopping is like this. This is the hopping. If you use a time binding model, you are going to consider 6 nearest neighbor. This nearest neighbor are the nearest neighbor of the MO atom, and of course they're mediated, somewhat mediated through the S atom. But in this time binding model, there are only 3 nearest neighbor, A and B, only 3. Okay, and here you have 6. So the band gap in MoS2 is due to the energy gap between the D plus and minus 2 and D0 states. So these are the states inside the atom. So the MoS2 band gap is from the atom, because if you go to our PowerPoint, where's my PowerPoint? If you go to my PowerPoint, this is the, I mean, not exactly due to the atom. Okay, okay. So first, okay, let's go check the origin of the band gap. The origin of the band gap is this. If you only have a 1 MO atom, all the D states, they all have the same energy. There's no energy gap. Okay. So once you put the MO atom in the trigonal prism surrounded by 6 S atoms, the sulfur atom, they're going to form a bond. That effect is large. Okay. Chemical bonds are large. Okay. So once they form a bond and then they have a significant effect, I mean, not just the bond, it's also a lot of crystal field all combined together. They will lift the degeneracy of the D state into 3 levels. Okay. And this 3 level, if you do the time binding model, okay, then you're going to get a band structure like this. If you don't consider the hopping, then the energy gap will be at the gamma point. So this energy gap is due to the influence of the S atom. The S atom open the band gap in MO atom, open this energy gap in the MO atom. Okay, But this is not the band gap yet. This is larger than the band gap. I mean, band gap is from band edge to band edge. So you need to consider the hopping, the hop to the K state, and then the gap gets smaller, and this is the band gap. So it's about 1 point something EV. So you need to know that the band gap formation in MoS2 is not the same as in graphene. Graphene is very simple, A and B sublattices. The difference that is, you apply potential between them, then you open the gap. But here is not. It's due to the S atom affecting the MO atom, and then combined with the hopping effect, then you open the band gap. And this is 1 point something EV. That's the reason for the band gap. So the band gap are different. And the second thing is, of course, this wave function. The two components is different. For MoS2, for graphene, the wave function is on the A and B sublattices. But for MoS2, the wave function is just on the wave function is on the D+2 and D states. So A and B. So here both A and B are in the same site. Okay, I used to learning the wrong way because actually I keep this mistake for many years, because I learned graphene, I know this Hamiltonian, and then later when I read the paper, people find that MoS2 also follow the same Hamiltonian, and then I was thinking, okay, they're just the same thing. And MoS2 certainly you have a band gap opening because this is S atom, this is a MO atom. They're different atoms. Certainly they have very different potential. Then they open the band gap. So I was thinking that MoS2 open the band gap because you break this A and B symmetry. But later when I mean just this time when I learn it more carefully, like I find oh, it's actually very different. This both A and B are in the same site. The band gap open because they're two different orbits split because of the surrounding environment. And even the hopping are different. They're hopping from MO atom to MO atom in a nearest neighbor time binding model. So graphene is somewhat different. So although both of them follow the direct equation, but the physics is not the same. And of course, one of the most significant difference is the spin-orbit coupling in graphene is negligible. Negligible. So we have learned spin-orbit coupling is proportional to Z to the power 4, right? Z is the atomic number. Okay, that is another difference. So overall, I think that is the comparison. Do you have any questions? Okay, if no, then we will end the lecture here. Thank you very much.